Hi friends, in this video we will discuss some topology problem of NBHM exam 2005. The first question was given that let f0 to 1 to r, open interval 0 to 1 to r, be continuous. It can be extended to a continuous function f tilde from closed interval 0 to 1 to r if and only if it is dash. So that should be, this is a simple example of a uniform continuous. So if the function f is uniformly continuous, then we can extend this function. And if it is not uniformly continuous and simple continuous, you cannot. For example, you can take as an example fx equal to 1 by x. So then it is not defined at 0. Not defined at 0. So this is the first question. The second question, consider the disjoint closed sets in R2 given by A equal to xy belongs to R2 such that y equal to 0. So what is y equal to 0? Y equal to 0 means simply your x-axis. And B is xy belongs to R2 such that xy equal to 1. So xy equal to 1 means this is the equation of a hyperbola. So drawn in the red color. So this is B and this is your A. So what should be written? This x-axis is an asymptote. So this thing is going very near to this x-axis. So distance will be 0. Third question, let f from 0 to 1 be such that fx minus fy is less equal to half of x minus y. So this is a contraction map. So we can use Banach's contraction principle, and Banach's contraction principle says that if T from x to x is a contraction map on a complete metric space xt, here your domain 0, 1 is a complete metric space, is a closed subset of R. So therefore it is complete metric space. Therefore it has exactly one fixed point. So let take the question a equal to x belongs to 0, 1 such that fx equal to x. So they are asking for how many fixed point has this. So this is exactly one fixed point. Third question is very easy. It is given that f from 0 to 1 be continuous such that f0 equal to f1 and all such t comma s belongs to 0, 1 cross 0, 1. So t not equal to s and ft equal to fs. So you just then how many elements of in A? So A has infinite many elements. Simple, you take fx equal to some constant function c. So then ft equal to c, fs equal to c. Therefore, ft equal to fs for all t comma s. And this is a continuous function. So this set has infinitely many points. Fifth question. GLNR with usual topology of Rn square is what? Open, close, connected, dense. So GLNR with usual topology, we can think as any matrix can be thought as a topological subspace of Rn square. You just like write them in a component wise. For example, if you have a 2 cross 2 matrix, some A, B, C, D, then you can simply write it like a B, C, D. So this is an element of R4. So an R4 has a usual topology, so you can use this topology. Similarly for GLNR. So GLNR can be identified with Rn square. And consider the map, determinant map GLNR to R. So whenever you are taking a matrix, its determinant is a real number. So, and what is your determinant map? You are just adding, multiplying. This is just a polynomial. So determinant map is continuous map. This is, just remember, determinant is a continuous map. And what is the image of the determinant? So determinant of GLNR is, this is a set of all non-singular matrices whose determinant is non-zero. So this is R minus 0. Therefore, we can write GLNR equal to determinant inverse of R minus 0. Now, what is R minus 0? R minus 0 is a open set. So R minus 0 means if you just lay a line like this, you just omit this 0. This 0 is not here. So maybe I can use some more darker pen. So this is 0. So now R minus 0 is open. This is a union R minus 0. You can write R minus 0 is equal to minus infinity to infinity. This is an open set. Union 0 to infinity. This is a union of two open set, therefore open. Hence, open and determinant is continuous. So what is the definition of a continuous? Inverse image of a open set is open. Continuity definition. Continuity. What is the definition of a continuity? So inverse image of a open set is open. So R minus 0 is open and GLNI is the inverse image of continuous inverse image. So this is also open. And GLNI is not connected, because if GLNI is connected, then its image under continuous map has to be connected, because we know the theorem that in continuous image of a connected set is connected. But GLNI is not connected. It's a two component. One is this positive negative component, one is a positive component. So GLNI is not connected. Next, GLNR is dense. Obviously, GLNR is dense because determinant of GLNR is R minus 0 and R minus 0 is dense in R. So GLNR is also dense in Rn square. The fifth question. Sixth question. So A equal to FB, which is a subset of X, and B equal to given by this. So I draw. So B is like a annulus. So annulus means this is a closed and compact set. Because what is the definition of a compact set? Closed and bounded in Rn. So it is closed, compact, and connected. So its image also will be closed, compact, connected. It is not dense. Obviously, it is not dense. There are so many points are excess. So this is only compact, connected. A compact means this is also closed, and this is not open. Because if you take simply the constant function, if you take f equal to constant, then whole thing goes to a point, and point is not open. So open is not, it is compact, connected, and you can say closed also. The seventh question, that A equal to x minus x naught, where x is an arbitrary Hausdorff topological space x naught belongs to x, then A is open, closed, connected, dense. Since x is Hausdorff, it is also T1. And what is the definition of a T1? In definition of a T1, we know that every singleton set is, this implies every singleton set is closed. So this singleton x naught is closed. So x minus x naught is open. So obviously this may be connected, may not be connected. These are options are not true. Eighth question, let FB is a subset of R, where R is a closed interval contained in 0 to infinity, and Ft equal to log t. Then A is open, closed, connected, compact. So Ft equal to log t is continuous. So it is given that B is on closed interval. So B equal to something like A comma B, either A comma B, or it is not bounded, or it can be some A to infinity. Here it is closed. So these two possibilities can be. So if B is closed interval, B is connected. Intervals are always connected, and log is continuous function. So image of log is again connected because B is connected. Suppose B is like B equal to A to infinity, then B is closed, but it is unbounded, so it cannot be compact. And if B is not open, clearly, because if B is your closed interval, whatever the case, FB has to be closed. This is a 9th question. So it is given A equal to xy belongs to R2 such that y equal to mx, excluding this 0, 0, which is subset of R2, is open, close, connected, nowhere dense. So look, y equal to mx is a straight line passing through the origin. So this point looks like this. This is a straight line passing through origin, but 0 is taken out. So this has two disjoint components. So this is not connected. This is not connected. Also, this is not closed because 0, 0 is a limit point. So 0, 0 is a limit point. Therefore, it is not closed. And obviously, this is not open, because for open, you need to have some open interval u from R2, open interval u subset of R2. For any point x belongs to A, you have a x which is belongs to U, and U has to be set of whole of A. So R2 in R2 are open set are like a disk. So this disk are the line cannot contain a whole disk. So this is not open. And its interior is empty, so it is nowhere dense. No, there is no interior point. The 10th and last problem, which is little bit difficult. A is the closure in C01 of the set B, where B equal to F belongs to C101 such that Fx mod Fx less than 1 and F dash X mod is less than 1. These two are given. Then A is closed, compact, connected, and dense. So to prove this, we use Arzela-Ascoli theorem. What is Arzela-Ascoli theorem says? What is Arzela-Ascoli theorem says? It says that a set of equicontinuous uniformly bounded function on 0, 1 has a uniformly convergent subsequence. And whenever you have a uniformly convergent subsequence, then the set has to be compact. So look here, B, first condition is mod of x less than 1. So it is equicontinuous and it is also uniformly bounded. So continuous and bounded, so therefore it is compact. This set is compact. Since it is compact, it is close to. So now we show that it is connected. So before showing connected, we show that this is a convex set. So what is convex set? Convex set looks like this, that if you have 2 points, any 2 points, and you can join by a line, and the whole line has to be inside this space. So suppose, for example, this space is not convex. This is convex. This is not convex. Not convex. For example, if you have a point here and if you have a point here, you join them by a straight line, this straight line goes outside this space. So this is not convex. So by some simple calculation, you can show that this is a convex set. And since it is a convex set, this has to be connected. So let Fg belongs to B and lambda belongs to 0, 1. So convex, what is the definition of a convex set? Definition. So if Fg belongs to B and B is convex, then this lambda F plus 1 minus lambda G has to be belongs to B. This is the equation of a line passing through F and G. So this thing we need to show. Now it is given that mod of Fx less than equal to 1. So just multiply by positive number lambda, we can say that mod of lambda Fx this equals to lambda, and similarly mod of Gx is less than 1. Therefore 1 minus lambda mod Gx is less equals to 1 minus lambda. Now just add them and put the values. Simple, since Fx are mod Fx or mod Gx are less than 1, we just put lambda and we add them, this is less than 1. So we found that they belongs to B. Similarly for derivative, I just slow it down this video, you can check, pause and see that similar calculation, and you can say the second condition is also satisfied. Therefore B is convex, which implies B is also connected. And this is not dense, simply you can take fx equal to 5. So fx equal to 5 is not a limit point, because if you take this your set B and you have some neighborhood there, then intersection with f, suppose this is your f and you have taken a ball like this. So f and a value of fx is 5. So this, then here all the elements are there who has maximum value of 4 or 6, something like that. So now your for elements of B, all the elements of B are far away because they are in between, they are less than or equal to 1. So they cannot intersect this. So they cannot be limit point. So B cannot be dense. Hence B is not dense. So